this course and the way that I teach finance is very probability-centric. You probably realized from the lectures you've seen already in this class, there are many different approaches, many different methods that are used in finance. Stochastic calculus, partial differential equations, simulation, and so on. Okay, the classical derivation of Black-Scholes is, well, many, but it's a solution of a PDE. Okay, that has appeal to people. In fact, this is why, in some ways, quantitative finance is a broad church, because whether you're a physicist or a probabilist or a chemical engineer, all the techniques you learn can be applied. You know stochastic calculus, or you know differential equations, they can be applied. But the path that I take in this class is very much through the probabilistic route, okay, which is my background as a probabilist, as an academic, or a statistician as an academic. And this is, in particular, I think, a very elegant path to understand finance and the linkage between derivative products, which might seem contrived, and probability distributions, which are sort of natural things for probabilists. So this is what I'm going to talk about today, is really this link, which I call option probability duality, which in essence, in its simplest form, is just saying option prices, they're just probability distributions. Therefore, these complicated derivatives that people talk about, all these options, these financial engineers, these quants, these exotics, we're really just talking about probability distributions. And we can go between them, option prices to probability distributions, and back and forth in a very elegant way. And what I love about this subject in particular is that to get to that point where we see this duality does not need a whole framework and infrastructure of complicated definitions or formulae or option pricing formulae or so on. So that's what I'm going to try and do in this hour or so, is introduce this concept of option price probability duality and show how it's sort of a natural, so there's a natural duality that can be seen in a number of different ways. Okay, so we're going to need a few definitions that should be familiar to you. We're going to define three assets. We have a call option, which you know about, a zero coupon bond, it's called a ZCB. This is the one thing I haven't become Americanized on. I still call this Z. It's other things I've become. And then a digital option. Okay. All right, so what are they? Well, they're all going to be defined by their payout at maturity. Okay, so we're going to have some maturity, capital T, and some underlying asset, S, the stock with some price, ST. Okay, so we know that the call option has payout at T, so let's call payout at T. So T is some fixed time in the future. We'll change it in the future with some fixed time. This is simply the max of ST minus K and 0. Okay, that's the call option. You can go through the right to buy, etc., but clearly it's just value at maturity is just the max of ST minus K and 0. The zero coupon bond with maturity T is just something that's worth 1 at time T, so that's just payout 1. That's definition. So you can think of these all as definitions. And then the digital option is just the indicator function of ST being greater than K. Okay, so here T is the maturity, K is the strike. Okay, so T maturity, K is strike. Okay, and these are three assets. So this is in some sense the payout function. Okay, all derivative products can be defined in terms of a function. Well, not all of them. Many derivative products can be defined just a function of ST, and here are three functions of ST. Here's the identity one. Okay, and then I'm just going to get notation for their price at T less than or equal to T. We can think about little t as current time today, or we can think of it as some future time between now and capital T. And I'm just going to introduce notation. Every different finance book uses different notations, so just it's just C for call price with strike K at little t with maturity big T. Okay, just that notation. The zero coupon bond, the price at little t, let's call that Z. Okay, that's the price at little t. And the digital, we'll just call that D. Okay, so this is what we're gonna set this up. The notation, actually, you could have a whole lecture on why notation, different notation. K and capital T are actually embedded in the terms of the contract. Little t is my calendar time. So you might sort of think, why don't you put K and capital T somewhere else? Well, when you get actually to modeling derivatives, you like to be moving both maturity and a forward time and calendar time. That's why I just write it like that, but there's no. Okay, so C sub K, little t, big T, is the price at time little t of a call with maturity capital T and strike K. Okay. Right, Black-Scholes and other option pricing formulae are all about determining this, right, for t less than t. Okay, because clearly we know that the price at maturity is simply the payout, right? I mean, that's, again, just a definition. Okay, so that's trivial, but we want to find out what the price is at little t. Okay, so that's a whole path of finance. Black-Scholes and other option pricing methodology is working out this, but we're actually going to go down a different route. Okay. Right, so what we're going to do, we are going to construct a portfolio. So we'll consider as a portfolio of what? We're going to consist of two calls. Okay, we're going to have lambda calls with strike K. Okay, so I've just listed them out holding of, and everything is going to be with maturity capital T. So lambda calls with strike K and maturity T, and minus lambda calls with strike K plus 1 over lambda. Okay, we'll just consider that portfolio. It consists of two options. All right, well, its price at T, well, that's easy. Let's just write it in terms of what is lambda times the price of the call with strike K minus lambda call with strike K plus 1 over lambda. Okay, that's just by definition. That's its price at T. Okay, well, let's look at its payout at time capital T graphically. Right. Okay, so we know about call options. Right, the payout function is just the hockey stick shape, clearly. That's confusing to people from the UK because in the UK, hockey means field hockey, not ice hockey. And of course, hockey stick shape and field hockey looks very different. Anyway, that's you understand what the payout of a call is. Clearly, this payout function of a call looks like this. Right? Okay. Well, putting this payout of lambda calls at strike K minus lambda calls at strike K plus 1 over lambda. Let's assume lambda is positive for the time being. What does it look like? Well, it's 0 below K. It's flat above K plus 1 over lambda. It has slope lambda. Okay. And has value 1 here. Okay. All right, you should be able to see that easily. Okay, so that's the payout. This is called call spread. Right? Just the spread between two calls. Okay, it has this payout function. Okay, so natural thing to do here, it being a mathematics class, let's take limits. Just let lambda tend to infinity. Okay, so okay. Well, then this becomes the partial derivative of the call price with respect to K, or the negative of it. So this tends to minus. Okay. Right, let's just. Okay. So that's that. And then this, of course, as lambda goes to infinity, this stays at 1. So this tends to payout function that looks like that. Okay. Right. Okay, so this is easy calculus. This is just by inspection. Right. Okay, so this clearly is the payout of the digital. Right. So. All right, that was strictly a digital call, but that's called the digital option. Okay. Just as a note, here's just greater than. You might think, okay, does it matter if this is greater than or equal to? Well, in practice, the chance of something equaling a number exactly is 0. I mean, if it's a continuous distribution. Well, in theory, I should say, the chance of something actually nailing the strike, actually being equal to k, is 0. So it doesn't really matter whether you define this as greater than or equal to. But in practice, of course, finance is in discrete time, because you don't quote things to a million decimal places. Right? So certain assets, actually, which are quoted only in 8ths or 16ths or 32nds or 64ths, this matters, actually, whether you define it as greater than, greater or equal to. But theoretically, it doesn't make any difference. Okay, so we've got the call spread tending to the digital. Okay? All right, so this tends to, so the limit of this call spread, of this price of the call spread, is the digital. And so we know that this is the price at t, this is the payout at capital T. Okay, the price of the digital must equal just the partial derivative with respect to strike of the call price. Okay. All right, so that's just a nice little result. Where does this bring in probability? Okay, so this is the next. Okay, so this is where we'll make one assumption. And it's actually a very important and fundamental assumption. And it's fundamental because it's called the fundamental theorem of finance, or the fundamental theorem of asset prices. So I call this FTAP, fundamental theorem of asset pricing. By this theorem, which we're going to assume here, the intuitive answer is correct, meaning that prices today are expected values, is the expectation of the future payout. Okay? So by FTAP, the price at T is the expected payout at time capital P suitably discounted. So there's both something very straightforward here and something very deep. Right? If you would think about how much would you pay for a contract that gives you $1 if an event happens, in this case the event being stock being greater than K at maturity, you would intuitively think that's related to the probability of the event happening. Right? How much would you pay to receive $1 if a coin comes up heads? You'd pay a half, probably. Okay. It's very, very intuitive. But the deepness is that this is actually holds under a particular probability distribution. I'm not going to go into that here, but by the fundamental theorem, this is true. Okay, so I can write, in the case of the digital price equals the discounted, and we'll explain why we want to put the zero coupon bond price here. That's the present value of $1 at time t. Right? Okay, that's just a discount factor. It's very trivial, but that's written in terms of an asset price times the expected value of the payout. Okay, so either you can take this as this makes a lot of sense, the discounted expected payout, or you can say, I don't understand this, I want to find out about the fundamental theorem of asset pricing, which we will prove in my class. But this is sort of intuitively makes sense. The key here, okay, is that the expected value actually has to be taken out under the appropriate distribution called the risk-neutral distribution. Okay. But this formula holds. In fact, strictly, I write this here just for what holds is that the price at time little t divided by the zero coupon bond, okay, is a martingale for those of you who are into probability theory. Okay, this gets probabilists very excited, of course, because they love martingales. Everyone in probability theory loves martingales. A lot of theorems about martingales. And you'll see, of course, that this is actually a restatement of this assertion. Okay, because Z capital D capital T is 1. Right? Okay, so this statement here is simply a re-expression of this martingale condition. Okay, so I just pause here just from a probability point of view. When I learnt probability, it was under David Williams, who wrote the book Probability with Martingales, which is a wonderful book, and I thought martingales is a great thing. So I was sort of happy. It took me about 7 or 8 years of being in finance to realize there are a whole lot of martingales floating around. Because this actual approach, this formalization of asset pricing, really only became embraced on the trade floor around the early 2000s, even though the kind of underlying theory was always there, this idea of these martingales. Anyway, so this is a... and this, of course, is simply... Okay, the expected value of the indicator function is just the probability of the event. Okay. All right, so now I've won by intuition. Just here's the probability of the payout occurring. I've priced the digital. I've also priced the digital by taking the limit of call spreads. Right? So now I'm just going to equate them. Okay. All right, so by equating these two prices for the digital, I simply get that the derivative of the call price with respect to strike equals the discounted probability of the stock being above K. Okay, I'll just reorganize a little bit, take 1 minus, and so I get the probability that, well, I can clearly reorganize. I'm going to get, all right, so if I want to simply get the cumulative distribution function, it's just 1 minus this. So divide here, take 1 minus. Okay, so I get the cumulative distribution function for the stock price at T is equal to 1 plus dC by dK times 1 over Z. All right, just rearranging. So here now is the cumulative distribution function. Clearly, I just need to differentiate again to get the probability density function. Right? So now here's where the little notation gets kind of messy, but clearly the probability density function of, so F, okay, for my random variable S sub t, right, so the density of, express that is, I always, funny problem is whenever you talk about densities, they always want to say f of x, and it's the same with me. As f of x, here's the density, is simply just the second derivative, or take the derivative of this, is the second derivative of the call price with respect to strike evaluated at little x. Okay, so. All right, so what we've done here is start off with simple definition of 3 assets, price to digital in 2 different ways, and now we have a rather elegant linkage between call prices, okay, C, and the density of the random variable that is the underlying stock price at capital T. Okay, so we've established one side of the duality, which is given the set of call prices for all K, okay, I can then uniquely determine the density of the underlying asset. Okay. Okay, so that might think, okay, this is kind of nice. How does this actually work in practice? do we actually think in terms of probability trading? Right? We just said that call options are equivalent to probability density functions. Well, actually, there's a very neat way of accessing this density function through another portfolio of options. Okay, so this is actually where we get, to me, a sort of practical relevance of some of this theory. So let me just show you that. Okay, so we're going to consider another portfolio. Okay, so here we'll consider portfolio as follows. Okay, it's actually going to be the difference between two call spreads. So lambda calls with strike k minus 1 over lambda. Okay. Minus 2 lambda calls with strike k. Okay. And lambda calls with strike k plus whatever lambda. Again, lambda positive. Okay. All right, why are we doing this? Let's just stop for a bit of intuition. Here, we've seen that the call spread is obviously the discrete approximation to the first derivative of call price with respect to strike. So clearly, if I want to approximate the second derivative, I'm going to take the difference between two call spreads appropriately scaled. Okay, you know I'm going to have there's going to have to be another lambda coming in here at some point. This is just the difference between two call spreads. So that's the difference between two approximations of the first derivative. So I'm going to have to scale by lambda in order to approximate the second derivative. Okay, so this is actually called a call butterfly. And this is a beautiful thing for two reasons. One is they actually trade a lot, surprisingly. This is not a contrived thing that I just made up. A, it trades a lot, so you can actually trade this thing. And the second is, as you can kind of imagine, the right scaling of this call butterfly is going to approximate this second derivative, and that's approximating the density function. So this is a traded object, kind of approximate the density function. Yeah.
Yeah, I have a question. But in real world, you cannot really, the strike distance cannot really go into like infinitely small. So they have some distant way. How can you approximate that?
Yeah, so that's a good point. We're not going to be, so the question is how, in practice, we can't go infinitely small, which is true. But we can go pretty small. So in interest rates, we might be able to trade a 150, 160, 170 call butterfly or equivalent, 10 basis points wide. That's it's a reasonable approximation to the probability of being in that interval. Okay, so these are all, you make a good point that, in fact, all of finance is discrete, in my view. So continuous time finance is done in continuous time because the theory is much more elegant. But in practice, it's sort of discrete in time and space. Okay? Right? You can only trade finitely often a day and so on. Okay. We'll go into the detail, but you can see the price. Let me just write down the price of this. Right, I will just express as the difference between two call spreads. So it's lambda times the call spread from 1 minus lambda to k. So k 1 minus lambda to k minus the call spread from k to k plus 1 over lambda. Okay, so that's the difference between two call spreads. We'll call this is the butterfly. We're just going to use temporary notation, call that B for butterfly. So the price B, and then you get confused. It's B centered at K with width lambda. No one ever uses this notation outside this one section of my class, so that's why. But it's just handy for this. So that is the butterfly price is equal to the difference in these two call spreads. What I want to do is I want to take limits of this suitably scaled to get the second derivative. And if you you need to take lambda times bk of lambda tt is indeed approximately, if I take limits, is exactly the second derivative. of the call price. Okay, so right, here's how I'm accessing the second derivative through a portfolio of traded options. All right, and so the price of this butterfly, B, if I just reorganize and substitute, okay, so I get BK for for large lambda, i.e. a small interval, okay, is approximately 1 over lambda times the density function. Okay. I actually evaluated at K. All right. So I have obtained this density function by this traded portfolio. And to your point about we're not getting infinitely small, that's absolutely right. But if you think about what the density, when you learn about density functions for the first time, you say the density function at x times a small interval is the probability of being in that small interval. All right. So when we think about the density function f of x, if we have a small interval of width delta x, okay, then clearly the probability of being in this interval is approximately f of x delta x. Right. Can't limit that is true. So what we're showing here, if you actually think about what interval we're looking at, we're actually looking at in this call butterfly, if you actually to draw it out, this call butterfly, looks like that around K. Okay. It actually is so it's a little triangle. It's not actually a rectangle, but it's a little triangle of width 2 over lambda. Okay, so it is actually, this is the area, right, of this triangle, right? It's 2 over lambda times a half times f of x, and that's actually this, right? So this has width 2 over lambda. Okay, so in fact we've got here exactly approximation. That doesn't sound right, but is entirely analogous to the approximation of the probability of being in a small interval. Here is the probability of being in this interval here. Okay, just the area under that is exactly 1 over lambda f of x. Okay, so here is actually something that people do, is they say, okay, I will look at the price of this butterfly, okay, which gives me the probability of this underlying random variable ending up around K, and I'll make a judgment whether I agree with that probability or not. And if I think that probability is higher than this price implies, then I'll do a trade. I'll buy it. I'll buy that butterfly. Right. So there is actually an active market in butterflies, and so I like to think an active trading in probabilities. Right? Probabilities of the underlying variable being at K, at maturity. Okay. Right. So so that's the first linkage here. Both the density is the second derivative, and the second derivative is essentially a portfolio of traded options. And none of this is dependent on the actual price of the call option, in the sense that this holds regardless. Clearly, this is a function of the price of the call option, but I don't need any model for the option price to hold in order for these relationships to hold. Right? So this is model-independent relationships, clearly. If you were to put the Black-Scholes formula into C, okay, Black-Scholes formula of the call price, and take the second derivative with respect to K, which would be a mess, you'll end up with a log-normal distribution, right? Because that's what actually the Black-Scholes formula is expected value of the payout under a log-normal distribution, and that will hold. Okay, so this will hold. Okay. Yes.
The last equation, so left-hand side depends on the small p.
Yes, it does.
But the right-hand side does not. What's the role of that?
Yeah, so it's a really good point, and I've been loose in my notation. So here, what is it? It's actually the conditional distribution of S capital T given S little t. So this is the conditional distribution given that we're currently at time little t with price S little t, or for the distribution at time capital T. So that's where it comes in. It's absolutely right. So in fact, a lot of this expected value, right, strictly should be conditional on ST. Okay? This probability is a probability conditional on ST. Absolutely. Okay. And in fact, this martingale condition is martingales with respect to S. T. Okay. Well, maybe. Okay. So that's where the little t comes in. Here, yes. Sorry. Yeah, there's 1 over z. That's right. It's just a constant here. This number, especially because interest rates are so low in the US. So this number is so close to 1 that you always forget about that. I mean, not when we're trading, but when you sort of, oh, well, that's just a... You just think about which one is... this is a quantity that's in the future, right? Because it's call prices. Okay, anyway, so that's how we're going to go. Okay, so... All right, so that's the first bit. When I was an undergraduate, actually learning probability, one thing I learned about probability was from my probability lecturer, who said the attention span of students is no more than about 40 minutes. So there's no point lecturing continuously for 40 minutes because people will start, they'll just start switching off after 40 minutes. So rather than just have a break and waste the time, the lecturer said, I'm just going to give you some random information in the break, and then we'll go back to probability. So I learned that from 25 years ago. I can't remember, I actually remember the material. I can't remember any of the random material. So that's what I do in my lectures, is break them up and talk about something random. So I thought I'd do that here as well, with some not completely random. So this is somewhat applicable, this being a maths class. So how many of you are math concentrators or applied math concentrators? 1, 2, okay, a lot. Okay. Applied math concentrators. Okay, especially for the applied math concentrators. Going straight to the conclusion. Your entire syllabus was generated at Cambridge University. That's the conclusion. So anyway, here's the story. So back in the 19th century, the Cambridge mathematics degree, the undergraduate mathematics degree, was the most prestigious degree in the world. In fact, it was actually the first undergraduate degree with a written examination. It was Cambridge mathematics, so they have a lot to be responsible for. And each year, people took the exam, and they were ranked, and that ranking was published in the Times of London, so in the national newspaper. And the people who got first-class degrees, so Summa degrees in Cambridge mathematics, were called Wranglers, and still are called Wranglers, actually. And the reason they're called Wranglers was from way back in the 17th century, where before they had exams, or the 18th century, I should say, before they had exams, instead of writing down an exam, you'd have to argue or dispute or wrangle with your professor to pass the class. So that's where wrangle comes from. So these people who got the first class degree called Wranglers, and they are ranked. And basically, the senior wrangler was a very famous person in the UK in the 19th century, and a lot of them turned out to be quite successful. So here are a few wranglers. I just got this one. I can't reach that there, can I? So some of them you might recognize, and then I just want to tell you a quick story about one of them. Okay, so let's start. So 1841, senior wrangler was George Stokes. So basically fluid dynamics, the whole of fluid dynamics, that's George Stokes. 1854, second wrangler. This is who was the first wrangler? The second wrangler was James Maxwell. So electrodynamics, Maxwell equations. He was the second. I mean, I can't quite work out who was the first. 1880, the second wrangler was J.J. Thomson. So electrons, atomic physics. That comes out of he was only second. 1865, senior wrangler Lord Rayleigh. So he was the sky is blue. He was first. Okay, so they're a pretty good bunch. So the best of 1845 are going back. The second wrangler was Lord Kelvin. So absolute zero, amongst other things, of course, but yeah, absolute zero. He was second wrangler. And the great story about him, he was the most talented mathematician of the decade. And he was such a lock for senior wrangler that, and I actually read the biography, so this is a sort of true statement, so that he sent his servant to the Senate House where these things were being read out and with a request, tell me who is second wrangler. And the servant came back and said, you, sir. And because he was such a lock to be first wrangler. And in fact, what happened was the question on the mathematical exam was a theorem that he had proved 2 years before in the Cambridge Mathematical Journal. So it's his theorem was set on the exam because he had not memorized it. So he had to reprove it. Whereas the person who became senior wrangler had memorized the proof and was able to regenerate it. And in those days, there was a lot of cramming to be done in these exams. So the guy who, Stephen Parkinson, was senior wrangler. He went on to be FRS and eminent, but so he wasn't. So anyway, so here you go. Here's the applied math syllabus. Here's a couple of other ones which I really like. So 1904, John Maynard Keynes was 12th wrangler. Now, I can tell this story either way, depending on whether I'm in an audience of economists or audience of mathematicians. Since I'm in an audience of mathematicians, I like to say, look, the greatest economist who was so poor at mathematics, he only managed to be 12th wrangler. There are 11 better mathematicians in the UK in that year. So he was obviously not that great. If I was talking to economists, I'd say, this guy was so brilliant that his main field was economics, and yet, as part-time, he was able to be the 12th best mathematician in the UK. So, anyway. All right, so the last one I wanted to talk about, 1879. All right, here's a quiz. This one you have to have some answers for. Okay, so 1980-something. I can't remember what it is. Okay, so here's 1, here's 2, here's 3. Right? I'm going to give you 1 and 2. You've got to fill in 3. Right? You're probably not going to be able to get this one yet. But anyway, so this is Andrew Allen, senior wrangler, George Walker, second wrangler, and number 3, the question. Okay, so that's the question. 1980, Hakeem Olajuwon, Sam Bowie, question mark. Okay, who's question mark? Do we know which sport these people play? Yes, right. There you go. That's Michael Jordan. Exactly. I think this question could go on forever in the UK because it does. So Michael Jordan famously was only picked 3rd in the NBA draft in 1984. Was that 4 or 5, something like that? Yeah. So now Hakeem Olajuwon was actually pretty good, but Sam Bowie was a total bust. So, but he was 3rd. So in 1879, in the Cambridge mathematics tripos, these 2 people you've never heard of were 1st and 2nd, and the person who came 3rd. You've probably heard of. I mean, this is more of a statistics thing. People know about correlation? What's the correlation? Who's the correlation coefficient named after? Pearson. Very good. Carl Pearson. So Carl Pearson was the 3rd wrangler in 1879 and the founder of statistics. He founded the first ever statistics department and obviously invented correlation with Gordon Pearson. So anyway, he was only the 3rd wrangler. And unfortunately, these people have very common names, so I have no idea what they went on to do. Right? Google these people is not very effective. Anyway, so that's the story of Cambridge mathematics. Lots of good stuff. All right, so the last half hour, I just want to go the other way. From where's my page 3? Okay, so the other way we went from option prices to probability. Let's go from probability to option price. We sort of already have, actually. This is what the fundamental theorem does. Let's take on trust that the fundamental theorem holds, namely option prices today are the discounted expected payout at maturity. Okay, let's take that on trust. Then we're going from probability distribution to option price in the following way. So let's actually state the fundamental theorem. FTAP. Okay, so I'm going to do general derivative D. It's D digital D derivative. It's so a derivative with payout at t. So this could be the digital payout, it could be the call option payout, it could be 1, and price. Right. Okay, so often we actually think about the payout function as just a simple function of the stock price. But this notation is useful when we think about the prices being martingales. Okay. Then, what is FTAP? D, the ratio of the price to the 0 coupon bond is a martingale. In other words, is expected value under the special distribution, risk neutral distribution, of the payout at maturity. And to your point, it's conditional on ST. So this is the proper statement. So this is the fundamental theorem of asset prices. In words, it's saying this ratio is a martingale with respect to the stock price under the risk neutral distribution. Okay. That's the statement of the fundamental theorem. This is actually rather neat to prove in a binomial tree, two-state world. It's very, very difficult to prove in continuous time. This is Harrison and Krebs in 1979. It's a proof that, however many times you look at it, you're only probably going to get through the 2 or 3 pages before thinking, okay, that's hard, but it's done. Okay, so this is, you can imagine continuous time, infinite amount of trading, infinite states of the world. It's very hard. Okay, so now this, of course, is 1. Okay, and this can come up. These are known at time little t. So if I'm thinking if I'm at current time little t, therefore the derivative price is what we had before, the expected payout. Okay, so this is a rather nice expression, and now we can actually just write down what this is. This is the expected value of a function of a random variable. Okay, so this is just the integral of g of x f of x dx, where this is the density of the random variable at time capital D conditional on being at st. So this conditional density. Okay, so this is a restatement of the fundamental theorem. So this is essentially the fundamental theorem, and this is a intuition made good, or intuition made real, expected payouts. Okay. This is sometimes called Lotus, the law of the unconscious statistician. It's just that the expected value of g of x is integral g of x f of x. That's not immediate from the definition of expected value. You should really work out the density of g of x, right? And then integral of x, the density of g of x dx. But it turns out to be this. Okay, so that's a very nice result. Okay, so here is now our way of going from density to price. If I put in the call option payout for g, and I have the density, I can then derive the price c. Okay, so if you like, the way I go from density to, or probability distribution to option price is exactly the fundamental theorem, or the route I take is the fundamental theorem. Okay, so FTAP, fundamental theorem of asset pricing, means I can go from the probability density to the price of the derivative for any derivative. Okay. All right. Okay, so now we can go either way. Density to derivative, or call price to density. You might say, well, hang on a sec, we've only gone from, we need the call prices to get the density. Well, of course, we can go via an intermediate step, right? So to get from the call price to an arbitrary derivative price, I just go via the density, right? So in particular, and this is restating, knowledge of all the call prices, okay, for all k, okay, determines this derivative payout for any g. Okay, so if I know all calls, I know the density, and then if I know the density, I know an arbitrary derivative price. Okay, it's obvious as we state it here. But what this is saying is the call options often introduces this, why are they important? Are the spanning set, right, of all derivative prices. So calls span, call prices span all derivative prices. And they're a particular type of derivative, the ones that are determined exactly by their payout at maturity. Right? One can imagine other things that are a function of the path or whatever, but this is a particular derivative price. European derivative prices are determined by calls. Okay, so that's kind of nice, sort of obvious, or it's elegant. There are two other ways of looking at this, though. Right? If I think about my function g, right? So consider function g. Okay, so that determines my derivative. So it defines the derivative by its payout at maturity. Let's just graph it. Okay, so it might look. Let's assume first it's piecewise linear, right? So it looks like. Right, suppose this is g. Okay. Well, you can kind of see I can replicate this portfolio, or this option, by a portfolio of calls. In fact, a linear combination of calls. Right? I have no calls, but if this is, say, K1, this is K2, K3, K4, K5, etc. Okay? You can see what the portfolio of calls will be in order to replicate this payout at maturity. Right? It'll be a certain amount of calls with strike K1 so that the slope is right, minus a certain amount of K2 to get this slope, plus a certain amount of K3, minus K4, minus K5, plus K6, etc. So in this case, so for piecewise linear G, replicating portfolio of calls is obvious. Okay. Right, so if I can replicate the payout exactly at maturity, the price at time little t of this derivative must be the price at little t of the replicating portfolio. That's actually I'll do that early on in my class, and of the 100 people, everyone's like, okay, that makes sense. And someone says, does that always have to be the case? And it's actually a really, really good question. Now here I was about to just hand wave over it. Is it the case that if I have one derivative contract with this payout at maturity, okay, and I have a linear combination of calls with the identical payout at maturity, capital T, must these two portfolios have the same value at little t? Well, one would think so, because it's right. They're both the same at maturity, so they must both be the same thing. They're just constructed differently. And the assumption of no arbitrage, which is, underpins everything in some sense what we're doing, would allow you to say, yes, indeed, that is true. Right? And in fact, it's actually the fundamental of finance. Right? If two things are worth $1 in a year's time, they've got to be worth the same today. Right? That's what we're saying. If you can match the portfolio at T, that is actually the definition of, it follows immediately from no arbitrage. What has been interesting in finance, especially since 2008, is that this assumption has broken down. In other words, I can hold a portfolio of things when aggregated have exactly this payout against an option with exactly this payout and be paid for that. Okay. And this is actually it's a very fascinating thing to think about actually the dynamics of financial markets when arbitrage can break down. What is the main theme here is that when capital T is a long way in the future, 10 years, 20 years, there's nothing to stop the price of the option and the replicating portfolio going arbitrarily wide other than people believing that it has to be equal. The only way that you can guarantee the two things to be equal is by holding it until capital T, right? For 10 years, for 20 years. In the meantime, those prices can move, empirically they've been shown to move away from each other. Right? So it's actually a sort of a deep economic question here. It's like if there is the presence of arbitrage in the markets, then that arbitrage can be arbitrarily big. Right? I mean, because you're saying there's not enough capital or there's not enough risk capital for people to come in and say, okay, these two things have to be worth the same in 10 years' time. Therefore, I'm prepared to buy one $1 cheaper than the other. It's actually a question really of relevance to the Harvard endowment. We're a long-term investor. You say, why doesn't the Harvard endowment, if these two things are $1 apart, buy the thing that's $1 cheaper and just hold them for 10 years, make the dollar? Well, we'd like to, but if we think that they're going to be $1 apart and they're going to go to $10 apart, we don't want to buy them at $1 apart. We want to buy them at $10 apart. I mean, yes, we're a long-term investor, but we care about our annual returns or 5-year returns. Suppose this is a 20-year trade. So this is very prevalent when these things are 20 years out. Anyway, it's a little bit it's a foundational issue. It's a thing where it could shake the foundational underpinnings of quantitative finance if you don't allow this replicating portfolio to have the same price as the actual option. But mathematically, you can see that you can replicate it, certainly at capital T, and therefore the price at time little t is just the linear combination of call prices. Okay, so let's assume that, and then obviously continuous function can be arbitrarily well approximated by piecewise linear function. Therefore, any function at time, any function with this of this form, a derivative with a payout of that form can be replicated by a portfolio of call options. So we can sort of hand wave to kind of say this must be true, that calls are a spanning set. Okay. There's another way to look at it, which is I just like from calculus, where we can actually make explicit what this portfolio of calls looks like in the arbitrary case. Okay, so let me just do that. So you can sort of see, okay, there must be a linear combination by this for a piecewise linear. Therefore, in the limit, any continuous function must be able to be replicated by calls. How many of each? Well, it's actually a very, very simple result. That is as follows. And, well, let's just write down an exact Taylor series, okay, to the second order. So this is so for any function with second derivative, let's just write down a Taylor series. Okay, the first two terms, and let's put the second term. We can just do an exact second order term. So 0 to infinity x minus c plus g double prime of c dc. C is my dummy variable. Actually, I've gone to plus notation. Here's the max of this and 0. Okay, so okay, that's an exact Taylor series. True for any. It's not an approximation. That's exact. You just integrate the right-hand side by parts if you want to verify it. Maybe it's obvious to you, but I'm so used to just doing non-exact Taylor series anyway. So this is the second order. So this holds for any g exactly. And now we're just going to make one little change, which sort of might make obvious what we're trying to do. I'm just going to take this dummy variable c, which we're integrating over from 0 to infinity, and just call it k. Okay, certainly do that. All right, this now looks like the payout of a call. Right. Okay. It's the payout of the call price. Now, I don't want to be integrating. Remember, if I want to actually get the call price, I take the expected value of this. I integrate x over x with respect to its density. Right? This is g of my payout function of x here. Here I'm integrating over k. Right? So I'm doing something a bit different. But this is the call option payout. Right? So this holds. It's a linear equation, obviously. And, of course, expectation is a linear operator. So I'm just going to take I'm going to do two steps. First of all, I'm just going to replace x with my random variable s sub t. Okay. So that I can do. This also holds. And formally, of course, s sub t is a random variable, so it's a function from the sample space of the real line. But if this holds for every point on the sample space, right? So I can write down this equation between random variables. Okay, here's just the integral over dk. Right, so that holds. Now I'm going to take the expectation operator. So take discounted expected value. Okay, so of each side, so in other words, what is my operator at each side? It looks like ZTT expected value of given ST. Right? Okay, so this one is the discounted expected value. That's the price. Right. So this becomes price of the derivative with payout at maturity G. All right, what do we have here? Well, first we've got a constant. All right, so we've got a constant times okay, so that's a constant. Okay, now we've got the discounted expected stock price. Okay, a little bit of thought on the terms of the fundamental theorem will show you that the discounted expected stock price under this operator is the current stock price. It's actually hand wave here is not non-trivial, but just think of the stock itself as a derivative, right, with payout S, and apply the fundamental theorem. Okay, this has to be the case because the replicating portfolio of the stock is just a holding of the stock. Okay, plus, and then we just take the integral, sorry, the expectation inside the integral. Okay, so now I've got discounted expected payout of this, and the discounted expected payout of this is just the call price. With strike K. Right. Okay, so I really like this formula. I mean, in some sense, it's nothing too complicated about how to derive it, but it says explicitly now, how do I replicate an arbitrary derivative product with payout G of X, or G of S at maturity? Well, it's clear. I replicate it by G0, 0 coupon bonds. Okay, so I have G0 of 0 coupon bonds. That's this. I have G prime 0 of stock. That's this. And I have this linear combination of calls. Okay. All right. So there is, it's kind of makes sense, right? You want the 0 coupon bond amount is just the intercept of G. The number of stocks is just the slope of G at 0. And then I have this linear combination of call prices. Okay. And I've just proved that by taking this and taking expected values. Okay. All right. So this is sort of a looking at the duality of call option prices and probabilities in different ways, but then also how calls span everything. So the calls, in some sense, are the primitive information. Once I know all call option prices, I know the probability distribution exactly. Okay. So there are a couple of sort of interesting further questions you might want to pose. We seem to have done everything here with regard to the distribution at time capital T, and that's true. I know all the calls. I know the distribution at time capital T. I know all the calls. I know the price of any option with a payout defined solely by a function at capital T. But I said nothing about the path that takes the stock from today until capital T. So I'm just going to leave you with two things to think about. Actually, it's one thing to think about. Two people thought about it a lot. Okay, and it's the following question, which now will start transitioning into stochastic calculus and stochastic processes a little bit. Okay, so we know, let's just imagine 2 times. All right. So suppose we know the set of all call prices with maturity T1, okay, for all k, and the set of all call prices with maturity T2 for all k. Okay, so then we know the distribution. Well, there are 2 distributions. We know the distribution of T1 given ST, and but do we know the distribution of the stock at T2 given T1? Right, more of a general point. Suppose I know this for all T. Let's put T0 here. Okay, I know all option prices of all maturities and all strikes. Okay. Can I determine the stochastic process for ST? Over this time. Is the underlying stochastic process for the stock price fully determined by knowing all call option prices for all strikes and all maturities? Okay. The marginal distributions or the conditional distributions for all maturities are determined because we know that here. Okay. Well, you probably see this is a rephrasing of sort of a finite dimensional problem from probability. The answer is no. And the reason to think about is if I know all the, my intuition for this is if I know all the distributions that, think about just a denser and denser grid of times that I know the distribution, we're getting closer and closer. I can still allow the stock to flip instantaneously, quickly. Imagine they're all essentially symmetric distributions and they're all roughly the same, expanding out. I can imagine the stock flipping discontinuously, right, over an arbitrarily small time interval. So without a constraint on the continuity of this process or mathematical constraints on this process, you can't determine the actual process for the stock, even given all the option prices, call option prices. It's kind of a... Okay, so there are 2... so typically Emmanuel Derman, who was at Goldman Sachs, now at Columbia, and Bruno Dupire, who's, I think, still at Bloomberg. This is the early 90s. Basically determined the conditions that you need. And the basic conditions are this, just the stock has to be a diffusion process. If it is a diffusion process, the random term as a Brownian motion, then it is actually fully determined. Okay, and there's a really nice, elegant result. So this is what gets mathematically quite nice and a little tricky. But there's a practical implication of this as well, which is, in practice, I will know a finite subset of call options. Those prices will be available to me in the market. Okay, so they will be given. Okay, so one thing I know for sure is that even with a very densely set of call option prices, there will be some other derivative prices whose price is not exactly determined by that set of calls. Because in particular, I know that the set of calls does not determine the underlying stochastic process, even if I knew all of them. Right, so that's a very important thing for traders to understand is that even if I know a lot of market information, someone gives me, here are the prices of a large number of European options, European call options I can trade. There may be a complex or a non-standard derivative product whose price is not determined uniquely, simply by knowing those options. And that is one of the challenges for some of the quant groups. So anyway, with that is all I wanted to convey. I'm happy to take some questions, and thank you for your time and for having me. Appreciate it.
Yeah, I had questions about. I was just wondering. So you said the call or set of all calls basically spans space of all possible payouts, right?
Yes.
So I was just wondering, maybe if we could change and select some other such basis for spanning it. Instead of call, maybe some other kind of basic payoff that could still span the same thing, and maybe it's more easily tradable or something.
Yeah, that's a good. I mean, there must be many. If I can, but this, given that this is the simplest expansion of the function g, an arbitrary function g, and the second term comes in with this call payout, right? Gives us its elegance, right? Now, of course, if I know all the digitals, I know the cumulative distribution function, and therefore I know the density. So, I mean, the digitals do the same. And in fact, Arrow-Debreu securities, which are sort of building blocks, which is something that pays off one in a particular state, sample state, also are building blocks. So, yeah. I mean, in some sense, it could be. You can think about an arbitrary basis that will span an arbitrary basis of functions that will span any continuous function. I mean, in some sense, you could do it in any polynomial expansion. If I have a price of any of those payouts, then I've got my spanning set, right? But this is the most elegant one. Yes, last question.
A question about the last time I mentioned. We had the process for ST, so it's like very well because the market is incomplete, so you cannot sort of use call option to replicate the stock itself.
You can use a call option to replicate a stock.
Yeah, is it like because
as long as you have zero coupon, as you can see from here, I can just reorganize anything here to zero coupon bond stock, and a set of calls will span anything. With maturity T. What it's sort of saying is, if I have this strange process with jumps, right, and flips and discontinuities, then the market is incomplete. I guess is what this is saying.
Okay,
right?
yeah. Also, right. In this case, it's due to like incompleteness.
Yeah, I mean, in the sense of most finance, in fact, all continuous time finance will assume there's some diffusion process for the stock, which has some Brownian motion, there's some function here and some function for the drift term. Right? In that case, then all the call prices do determine. Right? But if you think there's some exogenous flipping parameter, right, that's my intuition for it. So that's why this is incomplete. So this will not determine. So in particular, I could know all these call prices, then I could determine a particular derivative product. It could be the number of times that in an arbitrarily small interval the stock is flips this many times. I mean, there's some you can create whatever you like for a derivative, then it would be incomplete with these calls. Yeah.
So in this case, go back to the previous question, as we just mentioned, the second order derivative of call option with respect to strike is give us the risk neutral density.
Yeah.
So in this case, it was not that risk neutral density is a particular instance of that, not rather it's not uniquely determined, right?
No, the risk neutral density is uniquely determined. The stochastic process for ST over all time is not stochastic. It's not uniquely determined. So this is uniquely determined. Oops. By call option prices. That is uniquely determined. Okay.
So
but knowing the conditional distribution of S capital T given S little t doesn't determine the process of the stock price to get there. I can think of infinitely many processes of the stock price that will give rise to this distribution. Okay. That's what's not determined. It's the terminal distribution is uniquely determined by the call option prices, nothing else.
So in this case, if we take real world data, so we'll get a particular risk neutral density for each particular stock.
That's correct.
Okay.
That's correct. All right. Thank you very much. Appreciate it.